start the analysis. Right? So today we will study the Cauchy problem for Euler and Navier-Stokes. And I will stick to smooth solutions in this chapter. And then we will see weak solutions, that means more irregular ones. So, what is the Cauchy problem? It means that we consider the Euler of the Navier-Stokes equation in the whole space. Can you hear me? So that's the equation, right? That we saw yesterday. We look at it for positive times. Space variable is in the whole space Rd, right? And the question is the following. If I prescribe the initial data, here the initial velocity field u0, can I solve the equations for positive times starting from this data? Okay, that's the Cauchy problem. And so the aim of the chapter is to see that if the initial velocity field u0 is smooth, there is a unique smooth solution, at least locally in time. After a while, the solution may lose its smoothness, okay? But we will guarantee that for a short time, the smoothness is preserved and you have a nice unique solution. Okay? Can I forget to show something again? And the constant density is taken to be 1. And also, last remark, I cover both cases. Nu equals 0 is Euler. Positive nu is Navier-Stokes. Okay, so first I have to tell you what I mean by smooth and what I mean by there exists a unique smooth solution. Okay, so that's first paragraph, statement of the results. So, for smoothness, I will use Sobolev spaces. Okay, so starting point is the Sobolev space HS of Rd. As you probably know, this is the set of functions in L2 with derivatives up to order s in L2. D alpha u will be in L2 for any derivation alpha less than s. And here, s is in N. And you know that it's some Hilbert space with the scalar product, classical scalar, L2 scalar product for u, L2 scalar product for the derivatives. Okay? So that's the starting point. We will measure smoothness with this kind of spaces. And of course, in the study of Navier-Stokes or Euler, you have divergence-free fields. Okay, so we will introduce a useful notation which is HS sigma, which will be the set of fields in HS which are divergence-free. And this sigma here is, that's like a Greek S, and it's for solenoidal, which means divergence free. that's 1. The sigma is here. Okay, so this is the appropriate functional spaces, and we will be able to state some existence theorem in this kind of spaces. Okay? But at first, the point is to get rid of the pressure. Okay, so we will use the Loré formulation applying the Loré projector. Okay, so we will use the formulation of the equation that we had seen yesterday with the Loré projector. How does the Loré projector behave in this kind of spaces? We had seen that in L2, it's a projector onto divergence-free fields. Okay. But it behaves also very nicely here, which means that you have this short proposition that I leave you as an exercise. When you look at the action of P over HS fields, it's again an orthogonal projection onto HS sigma, divergence-free HS fields. Okay, so it preserves HS regularity. You have an orthogonal projection in the L2 sense, but also in the sense of the scalar product of HS. All right. So now, okay, one more line saying that the decomposition, the Helmholtz decomposition that we had seen of a field V as PV plus some gradient field is still orthogonal, not only in L2 but in HS. So this Loré projector behaves very nicely in these Sobolev spaces. Okay, so now I can state two existence theorems, one for Euler, one for Navier-Stokes. So first theorem will be for Euler, taking mu equals 0. And actually I will focus on this one. You take some Sobolev regularity index S greater than d over 2 plus 1. D is the dimension. And you take an initial velocity field u0 in HS sigma. Then you can find some time capital T, possibly small, and you can find a unique solution U. U will be continuous in time with values in HS sigma. It will be C1 in time with values in HS minus 1 sigma. And it will be a solution of the Euler equation that we formulate, as I said, with the Loré projector. So it will be a unique solution of the following system: dTu plus P u dot grad u equals 0, and u at t equals 0 equals u0. So I take u0 in HS with S large enough, so for a smooth enough solution, I will be able to have, at least for a small time, a solution with values in HS. And this solution is unique. Okay. Okay, what about Navier-Stokes for positive mu? So for positive mu, you can state some similar result. Actually, you could do better, but I won't do it. So similar result. Except that now U is continuous in HS and is C1 in HS minus 2. That's because of the Laplacian. Okay, when you take the time derivative, you lose two derivatives. Okay. Whereas for Euler, when you take time derivative, by the equation here, you lose one derivative. Okay. That's expected. Okay, so now we'll try to give you the main ideas for the proof of this very classical theorem. So that's part B. As you see, there are two things, uniqueness and existence. Okay, uniqueness at this level is the easiest, so I will comment this first. I assume there are two solutions, U1, U2, two solutions of the, so I will do everything for Euler and for Navier-Stokes. This is really minor changes. So you take U1, U2, two solutions like in the theorem. And you take V, the difference between the two. Of course, you want to show that V is 0.